Two things happened in fusion energy this year, and I think most people don't fully understand why either of them is a big deal. So let me explain both, from the ground up. First, let me tell you what fusion actually is, because this part matters before anything else makes sense. Normal power plants, coal, gas, nuclear, they all work by releasing energy that's stored in something. Coal burns, uranium splits. That splitting of atoms is called fission. It works, but it leaves radioactive waste, and the fuel is limited. Fusion is the opposite process. Instead of splitting atoms apart, you push them together. You take two very light atoms, usually forms of hydrogen, and you force them to merge. When they merge, they release a huge amount of energy. Way more energy per unit of fuel than fission. The fuel is basically seawater, and the main byproduct is helium, not radioactive waste. Helium. This is what the sun does, every second. The sun is essentially a giant fusion reactor held together by its own gravity. That's where sunlight comes from. That's where all the energy hitting Earth comes from. The problem is, we can't build a second sun on Earth. We don't have enough gravity. So scientists have to find another way to hold the plasma together long enough for fusion to happen. And that's where it gets complicated. Let me explain what plasma is, because this word comes up constantly, and it's not complicated. Plasma is just matter that gets so hot that electrons get stripped off atoms, so you're left with a soup of charged particles. It's not solid, liquid, or gas. It's a fourth state of matter. The sun is plasma. Lightning is plasma briefly. When you heat hydrogen enough, we're talking tens of millions of degrees, it becomes plasma. To make fusion happen, you need to get that plasma hot enough and keep it stable long enough for the atoms to collide and fuse. The temperature you need is around 100 million degrees Celsius. That is hotter than the core of the sun. The sun's core is about 15 million degrees. So yes, we are trying to build something hotter than the sun's core here on Earth, in a machine. I find that genuinely hard to process, but that's what we're doing. Now, here's where it gets tricky. You can't put plasma in a regular container. At 100 million degrees, it would instantly destroy anything it touched. So scientists use powerful magnetic fields to create an invisible cage. The plasma floats inside this magnetic field without touching the walls. The device that does this is called a tokamak. It's shaped like a donut. The magnetic fields run around the inside of that donut shape, trapping the plasma in a ring. This is confirmed physics. This is not theory. Tokamaks have existed since the 1950s. The question was never, does this work? The question was always, can we make it work well enough and long enough to produce usable energy? Which brings me to what South Korea just did. South Korea has a tokamak called K-STAR. It stands for Korea Superconducting Tokamak Advanced Research. This is a real, working fusion device operated by the Korea Institute of Fusion Energy. In February 2026, K-STAR held plasma at 100 million degrees Celsius for 102 seconds. That's confirmed. It was verified independently by the International Atomic Energy Agency, the IAEA, which is the global nuclear watchdog. This is not a claim from one lab. It's been checked. Now let me tell you why 102 seconds is impressive, because the number alone doesn't tell you much. K-STAR's own previous record was 48 seconds. They more than doubled it. In one go. That's not a small improvement. That's a leap. And the reason time matters so much in fusion is this. The longer you hold the plasma stable, the more fusion reactions can happen. The more reactions, the more energy you can extract. If the plasma collapses after 2 seconds, You can't get useful energy from it. You need it to stay stable long enough for the whole process to run. Think of it like boiling water. If you can only apply heat for 2 seconds, the water never boils. You need sustained heat long enough to reach the goal. Same idea here. The plasma needs to stay hot and stable long enough for fusion to produce more energy than you put in to create it. 102 seconds is a real step toward that. Not the final step, but a real one. What I find interesting is how this was achieved. Kestar's improvements came from a combination of better magnetic field control, improved plasma shaping techniques, and adjustments to how the plasma is heated internally. The engineering here is extremely precise. Tiny changes in how the magnetic fields are configured can mean the difference between plasma that holds for 10 seconds and plasma that holds for 100. Now let me add the second milestone. And this one is different. Very different. This comes from a private company called Helion Energy. Helion is based in the United States. They've raised billions in funding. Notable backers include Sam Altman, who runs OpenAI. And Helion has a power purchase agreement with Microsoft, meaning Microsoft has literally agreed to buy electricity from Helion once they start producing it commercially. That deal was signed in 2023. Helion's approach is different from Kestar. They don't use a traditional tokamak shape. Their device is called a field-reversed configuration, or FRC. Instead of a donut shape, it accelerates 2 plasma rings toward each other from opposite ends and slams them together in the middle. It's a more compact design. The idea is that it could be cheaper to build at scale. Their 7th-generation prototype is called Polaris, and in early 2026, Helion announced that Polaris reached plasma temperatures of 150 million degrees Celsius. That is 10 times hotter than the Sun's core. And they also announced what they called net energy gain in controlled conditions. Now I have to be really careful here, because net energy gain means different things depending on how you measure it. Let me break this down, because this is where fusion news often gets confusing or misleading. And I don't want to add to that confusion. There are 3 different ways people talk about energy gain in fusion, and they are not the same thing. The first is called scientific gain, or Q greater than 1. This means the fusion reactions themselves produce more energy than the plasma absorbed. The plasma gave back more than it took. This is what Helion is claiming for Polaris in controlled conditions. This is a physics milestone. The fusion reactions are working at a positive energy level. The second is called wall plug gain. This means the fusion device produces more total energy than the total electricity you pulled from the power grid to run it. This includes powering the magnets, the heating systems, the cooling systems, everything. This is much harder to achieve, and Helion has not claimed this yet. The third is commercial net gain. This means you can build a whole power plant around this, sell electricity, cover your costs, make it economically viable. This is the ultimate goal. Nobody is here yet. Helion is at stage 1, scientific gain in controlled conditions. That's confirmed by their own reporting. The company itself is careful about this. They use the phrase controlled conditions deliberately. They are not saying they've solved fusion. They are saying the physics is now working in their favor at the plasma level. I think the way Helion has communicated this is actually honest, which I appreciate. Fusion news has a long history of overclaiming. The phrase, fusion is always 20 years away, became a joke because for decades, breakthroughs were announced and then nothing seemed to change. So when a company actually tries to be precise about what they've achieved, that's worth noting. Now let me add context with a third thing, because there's another milestone I should mention. This one came from the U.S. National Ignition Facility, NIF, at Lawrence Livermore National Laboratory in California. Their most recent notable result, from April 2025, showed a fusion shot that produced 8.6 megajoules of energy from just 2.08 megajoules of laser input. That's a confirmed 4-to-1 gain on the plasma side. NIF uses a totally different method called inertial confinement fusion. Instead of magnetic fields, they use 192 powerful lasers fired simultaneously at a tiny pellet of hydrogen fuel. The lasers compress the pellet so fast that fusion ignites. Think of it like squeezing something so hard it explodes inward and fuses. Its 8.6 to 2.08 ratio sounds amazing. And the plasma physics is genuinely impressive. But the lasers themselves require around 300 megajoules of electricity to fire, so the whole system efficiency is still deeply negative. The gap between fusion reactions working and power plant producing usable energy is still large there. This is confirmed. NIF does not claim otherwise. I mention all of this because I want to be clear. Different fusion approaches are at different stages. K-STAR is a publicly funded research reactor focused on plasma stability. Helion is a private company focused on compactness and commercialization. NIF is a government laboratory focused on fusion ignition science. They're all working on related problems, but from different angles. Now let me explain the biggest fusion project in the world, because you've probably heard of it. It's called ITER. It stands for International Thermonuclear Experimental Reactor. It's being built in southern France, in a place called Cadarache. ITER is a joint project between 35 countries, including the US, the EU, China, India, Japan, Russia, and South Korea. The total cost is around $22 billion, maybe more by now. ITER is a tokamak, a massive one. When finished, it will be the largest tokamak ever built. The goal of ITER is not to produce electricity. It's to prove that fusion can produce 10 times more energy than it consumes. A Q factor of 10. That would be the definitive scientific proof that fusion works at scale. In May 2026, the final components of ITER's central solenoid arrived in France. The central solenoid is essentially the heart of the tokamak. It's a massive superconducting electromagnet that sits at the center of the donut and drives the plasma current. Getting it to France is a confirmed milestone. Assembly is ongoing. ITER is not expected to begin plasma operations until the late 2020s at the earliest. What I find interesting about ITER is the contrast with Helion. ITER costs $22 billion. It involves 35 countries. It's been in development for decades. It still hasn't fired plasma yet. Meanwhile, Helion is a private company that built a working prototype, smaller, cheaper, faster, and is already claiming scientific net gain. This is not me saying ITER is bad. It's me pointing out a genuine tension in how we approach big science problems. Sometimes giant coordinated projects are the right move. Sometimes they're slower than motivated private teams with focused goals and financial pressure. Both approaches exist right now. Both are making progress. That's actually a good thing for the field overall. Let me now explain the regulatory side, because this happened quietly in late 2025, and it matters for what comes next. The U.S. Nuclear Regulatory Commission, the NRC, finalized a new licensing framework specifically for fusion devices. What changed is this. Before, fusion devices were regulated under the same rules as fission reactors. That made no sense, because fusion doesn't produce the same kinds of risks. There's no runaway chain reaction risk in fusion. If something goes wrong, the plasma just collapses and stops. There's no Chernobyl-style scenario. The new NRC framework treats fusion devices more like particle accelerators than like nuclear power plants. This is a big deal. It means the regulatory path to building a commercial fusion device in the US just got clearer and faster. Helion specifically benefits from this. They are a US company. This new framework is part of why private fusion investment is moving so fast in the US right now. This is confirmed regulatory news. The NRC finalized this in late 2025. It's public. Now let me explain why all of this is happening at once. Because it's not a coincidence. The science has been slowly improving for decades. But three things changed recently that accelerated the pace. The first is superconducting magnets. New high-temperature superconductors, materials that carry electrical current with near-zero resistance, have dramatically improved the strength and efficiency of the magnetic fields in tokamaks. Stronger magnetic fields mean you can confine plasma more tightly. Tighter confinement means more stability. K-Star uses superconducting magnets. MIT's private spin-off company, Commonwealth Fusion Systems, is also betting everything on this technology. The second is machine learning and AI. The plasma inside a tokamak is incredibly unstable. It wants to escape the magnetic field. In the past, human operators had to manually adjust the magnets in real time. Now AI systems can predict instabilities before they happen and make thousands of micro-adjustments per second. This is confirmed. Google DeepMind published research in 2022 on using reinforcement learning to control plasma shape in a tokamak in Switzerland. It worked. And that capability has only improved since. The third is private money. Venture capital flooded into fusion in the early 2020s. Helion, Commonwealth Fusion Systems, TAE Technologies, General Fusion, dozens of private companies now. They move faster than governments. They have to. Their investors need results. This competition has pushed the pace in ways that decades of slow government funding alone didn't. The combination of better magnets, smarter control systems, and aggressive private funding is why you're seeing multiple breakthroughs in a short period. This isn't luck. It's what happens when hard engineering problems get more resources and smarter tools at the same time. What I find most clarifying about this whole topic is understanding what still needs to happen before fusion powers your home. Here's what needs to work for that to happen. 1. Plasma needs to hold long enough, hot enough, consistently. K-Star's 102 seconds is progress, but commercial plants would need to run continuously or in rapid repeated bursts for years. 2. The total system, magnets, heating, cooling, everything, needs to produce more energy than it uses overall. No one is fully there yet. 3. The energy produced needs to be captured and converted to electricity efficiently. Fusion produces neutrons and heat. Turning that into electricity needs its own engineering, and it's not trivial. 4. The whole plant needs to be buildable at reasonable cost. Right now, even the most advanced prototypes are research machines, not power plants. None of these problems are scientifically impossible. They're engineering problems. Difficult, expensive, time-consuming engineering problems, but not mysteries. I think the honest position is, fusion is closer than it's ever been. The milestones of 2025 and 2026 are real, but closer than ever still means years, probably a decade or more, before a commercial fusion plant is producing electricity for a grid somewhere. Helion's agreement with Microsoft targets electricity delivery by 2028. That is an ambitious timeline. Many experts privately think it will slip. But even if it slips to 2030 or 2032, that's still a revolution in energy if it works. What I keep coming back to is the fuel question, because this is the part that makes fusion feel genuinely important rather than just technically impressive. The main fuels for fusion are deuterium and tritium, both forms of hydrogen. Deuterium is extracted from seawater. There is so much deuterium in the oceans that it is effectively unlimited for human timescales. Tritium is rarer, but fusion reactors can actually breed their own tritium using lithium, which is abundant. So you're looking at an energy source that runs on seawater and lithium, produces no carbon dioxide, produces no long-lived radioactive waste, and can't melt down. That combination, if it can be made to work economically, would be unlike anything we've had before. Not because it would instantly replace everything. It wouldn't. The grid doesn't work that way. But it would mean a clean, almost unlimited energy source that any country with the technology could use, without fuel imports, without geopolitical energy dependence. I want to be clear, that future is not guaranteed. Fusion has surprised us before by taking longer than expected, but the direction in 2026 is genuinely forward, not hyped forward, actually forward. So for me, the main thing I understand now is this. 2 separate real milestones happened in early 2026. K-Star held plasma for 102 seconds at 100 million degrees, and Halion's Polaris reported scientific net gain at the plasma level. These are confirmed. They're not the finish line, but they're real steps on a track that's finally starting to look like it leads somewhere in our lifetime.